Hello, my name is Atakan Aral. I am going to present you our paper titled Staleness Control for Edge Data Analytics. This is a joint work by myself and Ivona Brandic from Vienna University of Technology and Melike Erol-Kantarci from University of Ottawa. It is partially funded by FWF Start Prize 2015 for the Raccoon project. I would like to start my presentation with one of the use cases that we consider in our paper. It is electric vehicles and their integration into the smart grid. So smart grid is about automation of energy generation, transmission, and also consumption. It can save substantial level of energy through optimizations such as capacity planning, where as much as energy that is going to be consumed can be produced and wastes are avoided. Transmission planning, for example, green energy where it is excess can be transmitted to other places where it is needed. Or in case of integration with electric vehicles, another optimization can be charge planning, which concerns when and where the electric vehicles are charged. For example, to avoid peak load. Charge planning alone is predicted to save 110 gigawatts of energy, which is equal to 30,000 average wind turbines. All these optimizations, of course, required continuous collection and analysis of data coming from many sensors, smart meters, and sensors within electric vehicles. Analysis and data collection is particularly difficult in electric vehicles because of their mobility. We propose an architecture for electric vehicle data analytics, which involves roadside units, which communicate with nearby electric vehicles. And these roadside units are equipped with so-called edge servers. So in the edge computing paradigm, computational resources are brought from central location to the edge of the network, where the data is generated and also where the data is needed. The objective of edge computing is to achieve low latency, high bandwidth, and as well as enhanced privacy. So these edge nodes process the data collected by the roadside units and train local prediction models. This is, of course, a kind of geographically distributed machine learning architecture. We find out three challenges in this scenario, summarized as insularity, which concerns the limited range of roadside units. Due to this limitation, each edge server only have access to the data in its proximity. So it lacks the global view of the all environments. The second issue is non-stationarity, which is about the changing environmental conditions, such as weather or traffic conditions. So the trained models have to be updated online in a continuous way. The third issue, which is directly related to the mobility of the electric vehicle, is intermittent connectivity. So when the vehicle is in between roadside units or in a tunnel, for example, the data collected at the electric vehicle is not immediately accessible in any of the local models. We argue that these issues are not specific to the electric vehicles, but a general problem that we call edge data analytics. In edge data analytics, data sources, such as electric vehicles in the previous example, send continuously streaming data to the geographically distributed edge nodes, such as the ones in roadside units in our example. And these edge nodes train local prediction models. These models are updated continuously, and periodically these model updates, we call them local updates, are sent to a centralized parameter server. In the parameter server, they are turned into a more complex but also more general and more accurate model. And again, periodically, these models are broadcast to all distributed edge nodes. So in this work, we are interested with the frequency of this broadcasting process. And our goal is to achieve geographically distributed edge data analytics with minimum communication overhead. Particularly, we are interested with the communication between the edge nodes and the parameter server, where wide area network is utilized. And we also aim to have similar accuracy to core data analytics. These two objectives are obviously conflicting, so this is not a trivial problem. Moreover, the problem is also subject to the three challenges that I have just introduced. So the problem we are addressing in this work is called staleness control. So to define the staleness control, I will use the same example of electric vehicles, where I provide a timeline of arrival times of the electric vehicle updates to the parameter server with a small scale example of only 4 vehicles. And at the bottom, we have 3 alternative solutions, where for each solution we present charts for mean accuracy of the local prediction models over time. So in the beginning, each edge node has a model, but this static model, if it is not updated, its accuracy will drop over time. This is because of the model is static, but the environment is dynamic or non-stationary. So let's assume that at time t0, we have only updates from vehicle 0 and vehicle 1, where the updates from 2 other vehicles are delayed for some reason. So the first solution proposes that we immediately build a global model at time t0 and broadcast it to all edge nodes. This will result in a more accurate model because it contains fresher data. The second alternative is to wait for a while and to get at least one more update from one of the vehicles. So let's assume that vehicle 3 has access to the network faster. So at time t1, we have the third update. So we have more information and we are able to build maybe a more accurate model in this case in comparison to solution 1. But the problem is we have to tolerate the stale model between t0 and t1. And the third alternative, as you can predict, is to wait even longer and get all the updates possible and get the most general model at the cost of longer wait with the stale model. The problem here is that it's not possible to know these accuracy values or the graphs or the arrival times beforehand or before taking a decision. So in this work, we try to find an optimum solution by predicting these values. So we propose SCADA algorithm, which stands for Staleness Control for Edge Data Analytics. And the main hypothesis of this algorithm is that there exists an inconsistent point to broadcast during each iteration, where the trade-off between generality and staleness yields the optimum accuracy. So if we wait longer, the generality increases because we have more information, but staleness also increases because the model loses its freshness. And our argument is that there is no single optimum point, and it depends on many environmental conditions at each iteration. So this point is inconstant. So SCADA algorithm is based on a Markov decision process model, where we have states representing the arrival of the updates from electric vehicles. Of course, I am giving you the electric vehicle example here, but in the paper, we describe a universal model. So in this example, zeros represent delayed updates and ones represent arrived updates. So in our example that I showed in the timeline, in the beginning, we already have 2 updates. We have also 2 actions that transitions between the states. So the push action is about building the global model and going to the B state, which is the end state, representing broadcasts. Wait action, on the other hand, is for, as the name suggests, for waiting for more information before broadcasting. So if we choose the wait action from the initial states, we switch stochastically to either this state where the information from vehicle 3 arrives, or to this state where information from or update from vehicle 2 arrives. We can push in either of these states or decide to wait to get all the information. So by using numerous trials and reward values for each action, and using reinforcement learning, SCADA algorithm learns about the individual connectivity of edge nodes, their relative connectivity, for example, the order the updates come from, and the significance of their updates. So, for example, if an update is predicted to be not significant, it might not worth to wait for it. We have some design choices defined as non-functional requirements for SCADA that SCADA satisfies. The first one is it is autonomous, so it doesn't require any human intervention and automatically learns. The second is it is online, so it continuously improves and adapts itself to the changing conditions. The third one is it has no monitoring overhead. It works with the data already available at the parameter server. For example, it doesn't measure the accuracy value at each edge node. Finally, its computational overhead is also quite low, so that it can run in real time. So to evaluate SCADA, we define some evaluation goals. First, we want to know if SCADA makes timely updates. For this, we use the metric from the literature called age of information. Second, we want to know if these updates are significant. For that, we used another metric called value of the information of updates. We also want to know if SCADA makes mistakes or how many mistakes it makes. So a mistake in our case is a wait action where no more new information arrives. So you wait in vain and your model gets more stale, and at the end you don't get a better model. And all these decisions and optimizations are only meaningful if they result in high accuracy. So we measure the accuracy at the edge nodes for simulation purposes, for evaluation purposes, and using different metrics depending on the use case. We also compare SCADA to 4 algorithms from previous work and best and worst case. For the best case, we have synchronous, where all edge nodes are always synchronous. So this is similar to core data analytics in a centralized data center. And the worst case is disconnected, where each edge node is completely insular. It works with the data that is only available to it, and there is no communication as a result. Finally, we want to know these results we obtain, how sensitive they are to the parameters that we choose, such as training time or reward function. Of course, we have too many results to discuss all in this presentation. So I will give you only a subset of the experiments that we run. In this experiment, we have a simulation of electric vehicles. We use the real-world electric vehicle data from the Charge Car project by Carnegie Mellon University. We use the mobility traces of 10 electric vehicles for a period of 3 hours to simulate their connectivity. And for this, in network simulator, we simulate a road of 100 kilometers with 100 roadside units distributed uniformly. Then we have these connectivity traces, but this Charge Car dataset also contains energy measurements from the electric vehicles. And we use this data to train independent clusters. We use an algorithm that is widely used for streaming data called StreamKM++. And these independent algorithms only use the local data. Models are only updated by the decision taken by SCADA based on the connectivity traces. And the result of this cluster is energy consumption patterns. And this can be a very useful input to smart grids where charge planning can be optimized. So I will give you only 2 numerical results. In the first one, we measure the mean accuracy at the edge nodes over time of 3 hours, our simulation period. And this is the performance of SCADA in comparison to best and worst case. Around the middle of the simulation period, we see a significant decrease in the accuracy. And this is because of the unexpected changes in environmental conditions, such as weather inference or traffic. But SCADA can recover from this. And but for example, when there is no communication between the edge nodes, in case of disk, the recovery is not possible. We also observe that in most of the time, SCADA has comparable accuracy to sync. So it is comparable to core data analytics in terms of accuracy. We also analyze the trade-off between network overhead and accuracy. So for network overhead, we use a number of broadcasts per minute by each algorithm. So the sync algorithm requires almost 8 updates per minute, whereas disconnected one does not make any broadcasts at all. SCADA, with only 1/8 of the broadcasts, can achieve almost the same accuracy as synchronous case and much higher than the disconnected case and other baselines that I am not going to discuss. So there are a lot more results in the paper, obviously, and this includes comparison to baselines and sensitivity analysis and so on. We have a completely different use case that is online prediction of virtual reality headset movements. We also present a discussion of the family of problems that fit to our framework. And we also present the complexity and convergence proofs for SCADA through PAC learning framework. So to summarize, our main contribution is SCADA, which is a reinforcement learning-based algorithm that learns the connectivity and stationarity patterns in edge data analytics. It achieves comparable accuracy to core data analytics, yet with real-time decisions. And our main finding is that partial model updates can be sufficient for high accuracy, and they are highly effective for low staleness in geographically distributed edge data analytics. However, this is only possible when the synchronization periods are not fixed. So this is the end of my presentation. And if you have any questions or comments, you are more than welcome to contact any of us. And thank you for watching this presentation.